In this video, we're going to talk about Bernoulli's principle, and this is a pretty important concept in the biotransport class. So what is Bernoulli's principle about? So Bernoulli's principle relates to the conservation of energy, and it comes from the Euler-S equation, and we can see this S equation down below. So if we think about the different terms in here, collectively, all of these, we can call them as the total head. Oops, pen is not working. Okay. All of these together, that's the total head. Okay. And Bernoulli's principle basically states that there is a conservation of the total head as you move along the streamline. So if you look at the streamline picture on the right side, here we see that this is the direction of the fluid flow, the direction of the streamline. And there's two directions that we really care about when we see how the fluid is flowing, right? The first one is the direction that's En hat, and this is perpendicular to the direction of the fluid flow. And this other direction is Es hat, and that's the direction of the fluid flow. So the S equation, as we can see, right, the S implies that we care about the direction that's along the streamline. And what we're saying is that there's going to be a conservation of the total head, these components right here, as you move along the streamline, right? So there's a lot of types of problems in 3300, right? How do you actually know which one actually is a Bernoulli principle problem? And a good thing to look out for is if you see flow through a constriction, then you can be sure that Bernoulli's principle will be applied in some shape or form. Now, that doesn't mean that this will be the only concept applied. I mean, of course, the problem could be a bit, bigger, and there's a lot of other things going on, so you may need to do other equations, but Bernoulli's principle, you can be sure you need applied if you see flow through a constriction. So how do you recognize flow through this constriction? So you'll have some sort of, like, for example, maybe a tube, and you'll find out maybe there's a blockage, or maybe you pinched it or something, and it can't make as much fluid flow through it anymore. There's not enough area, right? So you have this constriction point right here, so you can't have as much stuff flowing through as you can right here. Let's say this was area 1 and you have area 2, and maybe, just bring back up to that area. Area 1. This is also area 1. Okay, so you have this pinch point, right, which has this area. It has less area than area 1, so you have less amount of fluid that can go through it, right? And so what happens is you've essentially decreased the area. In effect, you actually also decreased the pressure. So pressure 2 is less than pressure 1. But you actually ended up increasing the velocity, which is kind of nice, right? And actually, to make it more concrete in your mind, if you think about your garden hose, right, and you want to make the water like shoot out faster and go a little bit, farther distance, what do? You actually end up putting your thumb over it, right? So you have like the nozzle, right, and you kind of block some of the area, right? You put your thumb over it or something, right? You block some of the area. So now you have, the water has less fluid to come out of the area, come the nozzle, right? And what happens is you ended up decreasing the area, decreasing the pressure, but you ended up increasing the velocity, so the water shoots out faster and it goes a farther distance, right? So that's kind of what happens in a lot of Bernoulli's principle problems. You have this like inverse relationship between your pressure and your velocity, right? As one increases, the other has to decrease. Okay, so there are some conditions you need to when you have Bernoulli's principle, that you're going to apply, then you have to make these assumptions, basically. You can't just use Bernoulli's by itself. You have to make some of these assumptions so you can simplify terms and things like that. And the first one is that you're going to ignore the effects of viscosity, right? And viscosity induces friction, so you're going to ignore friction, you're going to ignore viscosity by saying that this is lossless. Also, you're going to state that the system is at steady state. So meaning that some quantity, whether it's like concentration or something, it doesn't basically change with time. Also, you have incompressible flow. So that means you're going to maintain a constant density throughout the fluid. So it's like if you have, the fluid flowing through the pinch point, you're not going to like ended up decreasing the density just because you subject it to a smaller distance or something like that. The density stays the same, right? And lastly, your flow is going to be along a streamline. In most problems that I personally have seen, usually it's always a straight line. I think there's a few examples where it can be curved, but most problems typically tend to have like a straight line. So, you have like your point 1 somewhere up here and point 2 down here, or if point 1 is right here, maybe point 2 is like that. So it's like a straight line, basically, connecting the two. Okay. And actually, this is kind of important. So if you go back to the Euler-S equation, right? So if you were to effectively integrate this equation from point 1 to point 2, right? Bring this equation here and you do with the ds. Interestingly, that's how you actually generate Bernoulli's principal equation, right? And we're going to see the equation in just a second. So that's why this equation, the S equation is important. That's why the streamline, the points, all of that's pretty important. Okay, so here's the Bernoulli's equation that we care about. And we're going to, in shortly, we're going to like take this equation and we're going to rearrange some terms so we can really see that it's actually a conservation of energy. But first, let's just talk about the terms that we see in here. This P is referring to the pressure. The rho is referring to density. G is your typical gravity. And Z is actually at the height, okay? So like, for example, when you have something at this height and something at this height, right? We just care about what is the value here and what is the value here for the height, right? And notice we have like an equivalent term here as well. Same thing. Pretty much whatever is on the left side, we have it on the right side as well, just with the different prefix, okay? And then we also have a velocity term here, and then this is 2g on the bottom. Okay, and it's an equivalent thing on the left side. Now, we said that, Bernoulli's principle is a conservation of energy, right? And you look at this, and it's kind of hard to, how do you know that this is conservation of energy? It's just like the terms don't make any sense to me. I can't really see energy coming out of there, right? I don't really see how these terms represent energy. So now we're going to take these, and we're going to represent it in terms that we recognize for energy, right? And then we'll be able to say, yes, I can tell that this is a conservation of energy problem now. Okay, so the first term is I'm going to take the pressures out, and I'm going to say delta P. Okay, and basically by that I mean P1 minus P2. Okay, so P1, P2. So this is basically representing my pressure energy that's due to the pressure gradient. Okay, so this is energy, pressure energy, it's coming from the gradient. And then we're going to have half rho v1 squared minus v2 squared plus rho g z1 minus z2, and all of that equals 0. Okay, so if you look at this term right here, right, what does this term remind you of? If you think about it, you have a half, you have a v squared, and you have a rho, right? It kind of looks like the kinetic energy term, right? We know kinetic energy is half mv squared. And basically from up here and down here, besides the fact that we have a subtraction going on, right, it's like almost the same thing, right? The only difference is we have a rho here instead of an m. But if you think about it, density is mass per volume, right? And this is what the rho represents. It represents density. So you already have an m effectively here by saying the rho, right? So that we already see that, okay, we can then get kinetic energy out. So we see that. But there's like a little condition. It's actually per unit volume. That's the condition, right? Because you have this v also there in your density term. So basically this is kinetic energy. And it's per unit volume. And similarly here, as some of you guys may have been guessing, this is potential energy, right? And typically we see potential energy as mgh. Remember the z's, they are in fact a height difference, right? And that's what it is also in potential energy, right? You have like the ball up here or something, right? That's how usually the problems are. You have like a ball and it falls down, how much potential energy was there and all that stuff, right? So Z is referring to a height, right? So we have the height term here. And again, the rho is mass per volume. So this is potential energy per unit volume. And what we did here from up here, we had the left side equals to the right side. What we just did was we brought the right side over onto the left side. So that's what gave it the minus signs that we see here, right? And then we just said all of that equals 0, right? But pretty much in this representation, at least for me, I can kind of really clearly see that, yes, Bernoulli's equation really does relate to, the conservation of energy in various forms, right? Whether it's kinetic energy, whether it's the pressure energy due to the difference in the gradient, or whether it's potential energy in different forms, but we are still conserving the energy. Okay, so there are also some considerations you need to think about when you're doing these Bernoulli's equation problems. So actually, let's go back to the last slide. And we see there's a lot of terms, especially if you look in the red equation, right? You have 2 terms from the pressure, then you have the rho, then you have the 2 different velocities, you have the 2 different heights. It's a lot of terms, right? So it's sometimes a good idea if you can figure out how you're going to figure out these individual terms, because sometimes they're not going to give it to you that, oh, velocity 1 is this and velocity 2 is this. You may have to use another equation to figure that out. or they may not tell you the height difference. They may not tell you the pressure, right? So you have to use other concepts that you've learned in the course and, be able to come up with it. Or there are ways sometimes where you can just completely eliminate it altogether, right? So that's where these considerations kind of come into play. How do you figure out what some of these terms are? So if you see that both sides are exposed to the atmosphere, right, then you can cancel out the pressure term because, in terms of Bernoulli, we just care about what's the difference between the pressure. So I don't really care what P1 and P2 is by itself. I just care what the difference between the two is. And if they're both at the same pressure, whether it's atmospheric or any other pressure, if they're both at the same exact pressure, then who cares? It's delta P is 0. So I don't have to worry about it. And that's awesome because you just knocked out 2 terms from your equation. It makes life a lot easier, right? So then, if it's exposed to the atmosphere or any other condition where they're both the same, then the delta P is 0 and you just knocked out that term in the equation. Another thing is personally, from what I've seen, usually you have conservation of energy and then there's this conservation of mass kind of thrown in there as well, right? And that's what allows you to be able to use this equation, Q in equals Q out. Because mass conservation means you have m hat that's constant, right? But then you also have density is constant because of the assumption that we made for Bernoulli. And if you have both of these together, then you can use this equation up here. That your volumetric flow rate entering is the same that's getting out. Okay? So this is actually important because your volumetric flow rate is equals to velocity times area. Right? So, okay, this was a V. Okay, so you have a velocity times area, and we know for a fact that velocity is in the Bernoulli's equation. So maybe, if they're not giving you the velocity and they're not giving you the Q, or they are giving you the Q and they're giving you the A, then you may need to just rearrange these and solve for V, basically, right? So your V is Q over A, and maybe you end up plugging Q over A in the equation if you have to do something either with the flow rate or they don't give you the velocity directly, right? So there's a lot of these types of things you can do as well, rearrange things and then just plug in that in there. Okay, and the last thing is sometimes they may not give you the pressure right away. So it may not be as simple as the delta P is 0, but they're also not telling you, oh hey, the pressure is 1 atm here or something like that here, right? So you have to kind of go in and figure it out, and you may need to use a hydrostatics type. You may have another problem in there that's a hydrostatics component, right? So hydrostatic equation is you have the pressure that you care about is equals to the P naught plus rho GH. Right, so if you were to think you have some sort of a tank system or something, and maybe here it's connected to this arm, right? It's basically those manometer problems, and they'll tell you, okay, the height here is this, and maybe water is flowing out of this tube like that, right? But here they're telling you the pressure. They're not telling you what the pressure is, and you have to kind of solve it. So you'll have to use this type of equation, and this this P naught basically is referring to what's up here before you get this fluid that has whatever density. Right, before you get to this fluid right above it, that's what the P naught is. And typically that's usually the atmospheric pressure, but it just depends on the system that you have, right? So, these types of things, so they can kind of throw that in there as well. So that's why, these problems, they tend to not be an exclusion. It's not only exclusively just Bernoulli's and everything is just given to you like that. It's usually not like that. You have to kind of solve for other things and then plug it into this big equation, and then you get something else out. Okay, so, that was a lot of stuff we just talked about, right? Let's make it more concrete. We're actually going to look at a problem and see how we'll set it up and solve it. Okay, so here we have, this comes from Dr. Ethier's problem set number 5, and this is question number 2. And, it shows we have a barrel right here, and water is flowing out, so it's draining out from the bottom, exits to the atmosphere, and it forms a jet of circular cross-section, and this jet is basically tapering. So the diameter initially is 20 millimeters, but then it goes down all the way to 10 millimeters over a vertical distance of 50 centimeters. Okay, so there's a lot of stuff going on here. So what it means is you have a jet. So initially it's at 20 millimeters. And by tapering, what you're saying is it's getting narrower, right? Keeps getting narrow. And now the cross section is actually 10 millimeters, right? So effectively this is, this is kind of your hint, basically, to see that this is actually a Bernoulli's principle problem, because this is it's a masked way of saying, oh, hey, this is a, flow through a constriction, right? You're kind of being sneaky, but you're being told this, because if you think about what I mentioned before, when you have flow through a constriction, right, you have a tube and you kind of pinch it and then it's sort of like, it's kind of like this, right? Or maybe you have like blockage in your artery, but it's only like at a little place, right? And then it's kind of normal elsewhere. Well, it's kind of like, it's not kind of, normal elsewhere type of thing, right? So so what you're doing is you're just taking this problem and you're just kind of like looking at it from this side, right? And instead of like springing back up and becoming normal, it just keeps getting worse and worse. And that's why it's getting narrow. But basically it is flow through a constriction, right? You're just looking at half of it, right? You're just kind of looking at this side. So this is another way you can, identify a Bernoulli's, principal problem. Okay, and then here we need to find the flow rate. Okay, and also we're told the vertical distance. So the distance between these two guys is 50 centimeters, right? So vertical distance, right? Height difference, right? So basically that's what your Z1 minus Z2 is 50 centimeters. That's what it's referring to, right? And then we need to look at the Q, which is the volumetric flow rate. But then interestingly, we know that Q is equals to VA, right? And remember, in Bernoulli's, there's a term for velocity. So it seems like what we're going to do is we're going to plug in Q over A wherever we see a V, and then kind of go from there. And we're not told anything about the velocity. So basically, this is kind of where we start, and this jet, it's tapering down, and then this is kind of what we're told, this is like 10 millimeters. Right? So we say that, yes, it is a Bernoulli's principal problem. So we're going to say that, okay, since it's water, we're going to ignore the viscosity. We're going to say that it's at steady state. Technically, it's actually quasi-steady state here. So it's quasi-steady state. Because technically, water will speed up when it goes down. When you have less water remaining, it will speed up. But for this example, we're going to assume that it's not going to do that. It's going to flow out at exactly the same, rate, with the passage of time, right? So we don't really care that if there's less fluid remaining in the barrel, then it's going to flow out faster, even though in reality, that's what happens. So this is kind of our assumption, right? Quasi-steady state. It's lossless, and so we're going to specify our 2 points, right? So this is forming our streamline. It's a straight line. This is 0.1, this is 0.2. We know the height difference now, and we pretty much covered everything else, right? So we stated it's a lossless, we stated steady state, we talked about the streamline points. I think there's one more thing I'm forgetting. Did I mention everything? Oh, and yeah, okay. So we're assuming, you have the constant density, right? That's kind of given. Water, it's not going to change density when just because the jet is tapering. So that's kind of like already, it's kind of common, obvious. Okay, so now that we have that figured out, now what we're going to do is we're going to figure out how do we actually set up the equation for Bernoulli to figure it out. Oh, actually, there's one more thing. So we notice here, it says it's exposed to the atmosphere, right? So exposed to the atmosphere, that means that your delta P is 0. That's awesome. We just knocked out 2 terms from our equation. That is really, really awesome. Okay, so now we're going to write our Bernoulli's equation. We're going to get rid of the delta P, so we're not going to mention it at all. And we're going to write out what do we have to deal with now. So we have half rho V1 squared minus V2 squared. And that is equals to rho G. Oh, oops. Let me use the eraser. I meant to say minus. Okay. Minus rho G Z1 minus Z2 is 0. Okay. So what I just did was I just brought everything over to one side, that like the way I did before, right? I canceled out the delta P that would have gone here. So the delta P is gone. And now what I'm going to do is because I don't know the rho of the water, I don't have to look it up actually in this case because I see that there's a rho on both sides. So what I'm going to do is I'm going to make this side be on the left side, this on the right side, and I see that there's a density on both sides, and I'll just get rid of it. I'll cancel it, right? So I don't have to worry about the density of the water here. Doesn't matter. Okay, so I'm going to rewrite this equation. I have half V1 squared, minus V2 squared, and that is equals to G times Z1 minus Z2. But actually, there's a minus sign up here. Oh, actually, I just realized. So this was actually the plus sign. I'm sorry. This was the plus sign. Okay. And when we take that over on the other side of the equal sign, then we need to make sure we don't forget our minus sign. But actually, it's kind of annoying keeping track of this minus sign in front of it. So it's better. Why don't we just do this? What we're going to say now is to get rid of this minus sign, we're going to make this guy a plus, and we're just going to carry it in here. So we're going to say Z2 minus Z1 instead of the other way around. Okay, so notice it was Z1 minus Z2 up here. We rearranged it, right? just so we can get rid of this minus sign in the front, because it's easy to make a mistake and accidentally leave it off. So it's much more better if you could just keep track of the coefficients, the subscripts with the z's, and it's much easier to deal with now. All right, so now this is a lot more better equation to deal with. And the other awesome thing is we have 50 centimeters right here. We already told what the vertical distance is. So we don't actually even have to solve for z1 and z2. That's awesome. We don't have to worry about that. G is just gravity. We already know that. Okay, so your V1 and V2. So what do we plug in for those? Because if you look in the question, they don't tell you V1 is this and V2 is that, right? So what we're going to do is, since we need to solve for the flow rate, right? And since we don't know what the velocity is, why don't we just do this? Instead of putting V, we're going to put this rearranged V, okay? So since Q over A represents a V, and we have two V's here, so we have to kind of be careful. Okay, so let's go on the next page and we're going to figure out how do we write V. So we know that V, let's say V1 for now, is Q over A1, right? That makes sense. And actually, since the flow rate is the same for both velocities, we don't have to say Q1 and Q2. It's actually the same for both, okay? So, but then the area is different, right? Because we're told that the jet is tapering. So the diameter on one side is different from the diameter on the other side. So then that means the area is different. Okay, so we do need to, be explicit that area 1 or area 2. Okay, so we're going to do Q, but how do we actually represent the area? Well, if you think about it, we have actually a circular cross-section, and the area of a circle is pi r squared, right? So we have pi, but wait a second. We don't have the radius, actually. We just have the diameter, right? So diameter over 2 gives us the radius, right? And it's pi r squared. But then in this case, it's, the first diameter, right? And then if we actually expand all of this out, and actually in the Bernoulli's equation, we need to actually square the velocity. So let's square it. All of this stuff gets squared. Okay, but first I'm going to write this term out expanded with this square, and then we'll talk about that outer squared. Okay, so we have d1 squared over 4. So that gets us to, and we're going to just bring the 4 up here. 4q over pi d1 squared, and then all of that is squared. And that's what we're going to plug into our Bernoulli's equation. Okay, so then that gets us 16q squared over pi squared, and d1. So since it was already a squared, now we square it again, so we're going to get a fourth. Right? So that's what we plug in for V1 squared in Bernoulli's. And V2 is very similar. The only difference really is, instead of having any old area, we have area 2, right? And if you look here, the only thing that made it different between A1 and A2 is just this diameter, right? It's still pi r squared. You still have the pi. The 4q is going to stay the same. So basically, what you're going to do is you're going to do 16q squared over pi squared, and it's just d2 to the 4th. Okay, so if you plug all of this stuff, right, the 16q squared over pi squared d2 to the 4th for V2, and similar thing for V1 up here, right? We plug this in for V1, plug this in for V2 into our equation for Bernoulli's right here, right? So now we have these two terms. We already know that's 50, and that's just gravity, right? So it's just rearranging. So what we're going to have then is, because what we need to do is we need to solve for this q, right? So what we're going to do now is we're going to try to kind of sort of set it up for how the q would look like. Okay, so q squared, and technically because we're solving for the flow rate, we just need the q by itself. So it's like a square root of something. So now we're going to rearrange all these terms once we plug it in and rearrange it for q. And then if you just plug in the values, we should be able to get our answer out, right? So actually before that step, let's just do this. What I'm going to do is I'm going to write what the equation looks like before we take the square root of the q squared. Okay, so this is the half, rho v1 minus v2 squared. By the rho, we already canceled it out. So what we're going to do is we're going to do 4q squared, 16q squared over pi squared d1 to the 4th minus 16q squared over pi squared d2 to the 4th. Okay, that is equals to g times z1 minus z2. Okay, and notice we have a q squared right here and a q squared right here, right? So that's kind of what we're doing. We're pulling all of that out. So if you take that equation and you rearrange it and pull everything out, what you're going to get is you have g z1 minus z2 times d1 to the fourth times d2 to the fourth divided by 8 times d2 to the fourth minus d1 to the fourth. Right? So that's kind of, you plug in the diameters, d1, d2, plug in, your gravity, you plug in this difference, the vertical difference, the 50 centimeters, right? You plug everything in, and then you're going to get, in terms of centimeter units, you're going to get 254 centimeter cubed per second. Okay, and that's the flow rate that we're looking for. Right? So basically, what we did was we took our pressure, we took our components for, the velocity, we took in our the diameters for the area and the velocity, and we just put all this together, and we knew that, since it's exposed to the atmosphere, we just completely get rid of pressure terms in this case altogether. And, that's kind of how these problems work for Bernoulli. You just take these terms, put them together. If there's things you can cancel out, it makes life a lot easier. So make sure you always cancel things out. Okay, so I hope you find this, this video helpful.